I'm Joohno Lee from Robotics Systems Lab in ETH. And today I'm going to talk about our recent progress in applying deep reinforcement learning for this full-legged robot dog we have. So I'll skip the motivation for using four-leg robot. Everyone knows that it's very useful, very cool, nice robot. And yeah, so we have developed a very robust locomotion controller for this robot here. And these days we can go hiking with this guy, like even on this very rough terrain. And I would say this was not possible with the best model-based controller we had before. And in our recent work, we have achieved like state-of-the-art performance using deep reinforcement learning and by training the controller in the simulation. So yeah, today I'll mainly talk about this work. Yeah, and before talking about how we did it, and with the same controller, we were able to go like so many different kind of terrains, which is cool. So yeah, let me first explain like what is the control problem we are solving and how it has been done, and why we need to use RL in this like established field. So actually making a robot like this walk is a very difficult problem. The robot has to decide which foot to move at which timing, and it has to like balance, and there are so many external forces applied on the robot. It has to make use of the ground reaction force. It has to reject the disturbance. And yeah, so it's like multi-objective optimization problem. And like we have to solve this optimization problem on the robot, like in the real time with the small CPU on the robot. So and my task is to develop a nice controller which somehow perceives the environment or understands the environment, the robot, from the sensor information and decide how to move each joint. In our case, we have 12 joints. And people have been like solving this control problem by dividing it into two problems. The first one is the low level control, like tracking control. So like we say we have the nice trajectory of the robot that it has to follow. We know when to step, then the robot should be able to follow that trajectory. And there are many objectives that I like talked about before. And using the robotic, like by solving rigid body dynamics and using many established robotic controller, like robotic control method, I would say this is quite, we have like a well-established knowledge for solving this problem, like solving this tracking. So the robots can react to disturbance and it can follow trajectories very well. And the second problem is actually the generating the reference motions, like generating the walking motion. But the thing is, walking is not something we can easily formulate like mathematically, like continuously, because it makes a lot of discontinuous like interaction with the terrain, with the environment. It might hit the knee on the ground, and there are so many options. So, so people has been using trajectory optimization techniques using some reduced order model. So they could generate this kind of cool walking behaviors. But the problem is this kind of optimized trajectories are usually not very realistic. If you see the video here, it doesn't look very realistic, right? The robot actually cannot do that. So, and a bigger problem is generating this kind of motion in the real time is very difficult because you have to solve this very complex optimization problem. So what's been done to run this kind of like to generate motions on these robots out there is by handcrafting this kind of behaviors. So if you see these robots out there, they really do this very regular gait. That's because people like engineers define gait pattern, and robot only focuses on this following it. And there are many assumptions to simplify the problems. Like they assume that the contact only occurs at the feet, or the foot doesn't slip and hardly slips, and the terrain is usually like static. It shouldn't move when the robot steps on, and it's like planar. And to even simplify the problem, like they represent the environment in a very simple like representations, like binary contact state. So the robot knows if the foot is contact or not, or binary foot slip state. or some simple representation of the terrain. And this kind of method worked very well so far. Like if you see Boston Dynamics spot, it can do so many awesome things. And Animal can also do very nice things. Like it can do many different kind of gates. It can even jump. But these simplified assumptions often breaks if we take the robot out of the lab. For example, when the terrain is not static, the controller sometimes gives up because it's not something this is not something it somehow, we assumed when we designed the controller. And for example, when we take the robot to like forest where the foot slips all the time and there are so many disturbances from the like tree branches, the controller also gives up because it cannot understand the situation, because the controller never knows that there can be a contact in the shank or something like this. And yeah, if you want to take the robot to complex natural terrains like this, like we cannot design all the different motions for all kinds of different combinations of foot terrain interactions. And here is where we need to do RL. I'll not explain RL in detail because Yunlang explained it very well before. So what deep RL does is the agent or the controller randomly explores in this environment. It can be in simulation, it can be in the real world, but in our case we use simulation. And by interacting with the environment, it gradually learns to like discover the behaviors. And this is very nice for us because we can like discover walking behaviors without fine tuning or without no fine tuning is needed, but without like predefining gait pattern or without making any assumptions. So yeah, so before the controller was like this, there were predefined gait pattern and some gate switching mechanism and the tracking controller that follows this given gait pattern and like predefined motions. But now using the DeepRL, we could replace this using a neural network. And the cool thing is, as we use the simulated data and we have this very flexible neural network model, we could generate so many new behaviors that were not possible before. For example, like when I kick the robot, it lowers over the ground and it touches so many body parts on the ground. This kind of like, and there are so many contexts involved in this kind of motion. And this kind of motion was not possible with the model-based method, or could be possible, but very difficult because you cannot assume where the contact happens and everything. So yeah, that's why we are like, this video summarizes why we use RL to generate motions for like robots. So yeah, so in this work, we could like generate this kind of different behaviors in simulation using RL and could run it on the real system by developing a very nice simulator. So the next step is to train it on many different kinds of rough terrain because that's what we want with the animal. So we defined several different rough terrains in simulation. For example, like this hilly terrain and some steps and stairs. But if you just train it in simulation and if you try to like transfer it to the real system, it usually doesn't transfer that well because like, for example, we want to run this controller on the real system. Maybe it's hard to see in this video, but you can see that the robot shakes a lot and the motion is quite off from this motion. And the reason is that in this loop, in this control loop, the controller understands the environment from the some kind of simplified representation of the world. In our case, this simplified representation includes the state of the robot, like the velocity of the robot base and the joint positions and this binary context state. But this representation is not like strong enough to understand all kinds of different natural terrains. And in this case, this kind of context estimation also like has a lot of error, like it's not very accurate because this is something people tune and this is like like this kind of state estimation is somehow defined by some heuristic rules, so they cannot be applied to our kind of different controllers. So it is usually very unrobust and not expressive enough to apply it on the rough terrains. So what we did in our recent work is to replace part of this block using a neural network. So what we did is, in the robot, we have multiple sensors. We know the joint positions, we know the joint velocities, we know how well it's tracking the given like trajectory, and we know how like the pose of the base. So in this work, we like stack the like measurements of this proprioceptive measurement sequence of these proprioceptive measurements, make it into an image. Then when the robot walks, you can actually see there are like distinctive patterns, like repeating patterns in this kind of proprioceptive measurements. And then we process this proprioceptive measurement using a temporal convolutional network, which is basically a convolutional network which applies convolution in the 1D, like in one direction. In our case, we applied in this time axis, and extract some nice features and use this kind of nice representation of implicit representation of the world instead of using the binary context state or binary sleep state. And yeah, this was the architecture, like core architecture. And usually if you just want to train this kind of big network using RL, it is very like it's not very trivial, because like if you have more parameters, it is usually very sensitive to hyperparameters. So you have to like put a lot of effort in tuning the learning parameters, tuning the reward functions and everything. So we had to do some special learning strategy called learning by cheating. So what we did here is there was a cool paper called learning by cheating. This paper was for the autonomous driving. And what they did is they trained the privileged agent or privileged RL policy, which knows the exact state of the environment around this guy. So in this case, from the simulation, this car knows what the traffic light is and where other cars are. And we first trained this guy using imitation learning or RL or yeah. And as this agent knows are the like noise-free accurate like information around itself, it learns really fast and it achieves very high performance. And in the second step, they train the actual policy they want to run on the car. So what this agent gets is the image, only image. And by imitating the privileged agent, this sensory motor agent learns to extract this kind of necessary knowledge, necessary information from the image. So we applied the same strategy in our case. So we first train a teacher policy or privileged policy. And this policy knows the exact context state given from like noise-free context state from the simulation and contact force and terrain profile around the robot, friction coefficient. So everything we can give from the simulation. And we train this guy using reinforcement learning. And this network is just like 2-layered MLP. So it trains really fast and it achieves very high performance in like 8 hours, which is still long, but like relatively faster than any other, like training the whole TCN. And then we imitate this guy using the TCN network, which is much bigger, which has much more convolutional networks like layers inside. And this agent only perceives the proprioceptive measurement, like joint positions or base poses. And this guy tries to imitate the teacher policy. And by imitating the teacher policy, it learns to extract useful features from this proprioceptive history. Yeah. And to train this agent on the rough terrain, we need to define we need to provide good terrains to make it learn faster, right? If the terrain is too easy, it will just overfit to the flat terrain and it cannot like overcome any challenging terrain. And if the simulated terrain is too difficult, it will just fail all the time and will not learn anything. So what we want is something in between, something that's not super hard, something that's not super easy. So we define the measure, like performance measure called traversability, which is basically a success rate on the terrain. And we provide the agent with the terrains with the mid-range traversability during the training. We used particle filter here, which is basically a genetic algorithm. And with this method, we could provide like properly difficult terrains during the training. So at the beginning of the training, the terrains looks easy, and then it gradually gets more and more difficult. So with this method, we achieved like a very terrain adaptive, very robust controller. So we trained this and we like deploy this student policy on the robot. So yeah, we could go to so many different terrains. And cool thing about this method is we never simulated this kind of deformable terrains or slippery slopes in the simulation. But this TCN feature extractor learned very robust features from this proprioceptive history. It could adapt to so many different kinds of terrains, which were almost not possible with the existing method. And we did some controlled experiment. For example, when the robot gets stuck in this kind of step, it could step up, like it could react, it could like sense that there's a step in front of the foot by looking at the history of the joint measurement. And in the conventional approach, this could only be done by handcrafting this kind of reaction loops. So, and our approach just discovers it from simulation. And yeah, and as we randomize the terrain a lot during the training, we also randomize the terrain friction. Our controller can also adapt to like very slippery terrain. Here we put the whiteboard and pour water on it, and then it becomes super slippery. And then like as soon as the robot slips, it detects that here is the slippery terrain and changes the gate frequency and adapts. So we could like move in our direction on this slippery terrain. But usually in the model-based controller or like in this conventional approach, what they do is they have some heuristic rules to detect foot slippage. So they first detect foot slippage, and there's another handcrafted motion sequence to react to foot slippage, or like handcrafted constraints or something. But yeah, they don't like completely fail, but you can see that it completely loses the tracking performance. So yeah, with one single neural network controller, we could also handle this foot slippage. And during the training, we don't really randomize the mass or inertia of the robot model in simulation, but we apply many different disturbances during the training. And then like the robot, now the controller can actually react to different kind of disturbances by like from the feeling of itself. Like, so here we put 10 kilogram mass on the robot, weight on the robot, which is not like known to the controller, but the controller can still do the same thing because it already like experiences a lot of different disturbances during the training. So it could just adapt to like this heavy mass. But if you do the same thing to the conventional method, which like relies a lot on the model inside, if there is this kind of big model mismatch, the controller cannot just handle it. So if we command the robot to stop, it drifts away and it just easily falls over. So yeah, to conclude, like we could achieve like, yeah, by training in the simulation, we could achieve all these 3 different like adaptive behaviors in like one day. And one cool thing about our approach, our controller, is that when you talk to robotics people, like when we talk about the learning-based controller, people really hesitate to use it because it's black box and they don't know what's happening inside. So, but like, so we also have like, and we have this team in our lab, which goes for DARPA Subterranean Challenge, which is actually a like big challenge for robotics people. And they tried out our controller, and they figured out that this controller is much more robust than whatever the controller we had before. And now they are using our learning-based controllers in this real-world like setting. I think this is the first time the learning-based locomotion controller is used in this kind of real challenges. I'll skip some details of the method. So here let me summarize this thing. So here I somehow try to analyze what this TCN extracts from this proprioceptive history. And the cool thing is we could reconstruct the terrain profile around the robot, and we could really reconstruct the friction coefficient. So the TCN learns to like encode the friction coefficient of the terrain. And yeah, in many cases, having longer proprioceptive history, like performed much better. Yeah, as I used up all my time, I conclude here. So we achieve state-of-the-art performance in rough terrain locomotion using the neural network controller. And instead of using these handcrafted features like context state or sleep state, we just learned it, and it improves robustness and adaptability of the controller like much higher. And one cool finding of our work is we never simulated deformable terrains or like these tree branches or everything. We only simulated the rigid terrains with different shapes and some disturbances during the training. But the controller could still generalize well to different situations. So maybe we don't need very accurate simulation of the complex real world for like if we can train a very well generalized controller. And yeah, based on this work, we are working on many different like directions. The first thing we have to do is like what I did in this work was completely blind. So it's like walking in the dark. The robot just like relies on the feeling of the foot and adapts to different terrain. But we can mount more sensors on the controller, on the robot. So yeah, we are working on how to make this guy perceive the terrain and actually like foresee the coming terrain and more aggressively move. And yeah, during this work, we went a lot of field tests, and there we also collected so many data, like so many RGB image data, and we are still collecting many image data. So we are also working on visual navigation. And as this RL approach is quite generalizable, it can be transferable to different platforms because you can just change the model and change the reward function, and you can just basically apply the same thing. So there are people who are doing this thing in different platforms. So yeah, we are working very hard to come up with something more cool than this thing these days. And thanks. That's my presentation.